Right, so yeah, my name's Mairi O'Brien. I'm a PhD student at the University of Warwick in the UK, and I'm going to be talking to you about my work on the 40 parsec sample of white dwarfs that we got from Gaia. So as an overview, I'm going to talk about how Gaia has revolutionized our ability to find white dwarfs, how we went about constructing the 40 parsec white dwarf sample and the completeness of the sample and missing systems as well. And then I'm briefly going to cover some of the key results from the 40 parsec sample and some open questions that we could maybe discuss in the breakout sessions later. But before I start, I just wanted to give a disclaimer because I know that this talk is in the context of volume limited samples of cool stars, so I'm not going to give too much information on the details of the white dwarf science that we've done. More generally, two things that are important for white dwarfs are that they cool down as they age because they're no longer burning fuel in their cores. So they start off hot and then over time they cool down, which means that the temperature of a white dwarf is a reliable proxy for its age. So we can quite easily determine white dwarf ages. Additionally, due to the well-defined mass radius relation of white dwarfs, if we know the radius of the white dwarf, we can determine its age. So we can get masses and ages quite easily for white dwarfs. So why did we create this volume limited sample? I mean, a lot of people have been explaining already how useful volume limited samples are, but I think the most important factor for why we did it for white dwarfs is that we're able to probe an entirely different parameter space of ages. So if you look at the histogram on the right, at the top, you can see the brightest 1,000 white dwarfs as seen from Earth. And you can see that it's very biased towards hot and young white dwarfs. Whereas for the volume limited sample, which is the most nearby 1,000 white dwarfs, which make up the 40 parsec sample, we are spanning a whole range of ages. So we're looking at the whole of white dwarf evolution, which we just can't do with magnitude limited samples. So the 40 parsec sample is the largest volume limited white dwarf sample to date, which we have completed with spectroscopic follow-up, so we can determine the exact type of white dwarf we're looking at. And the plot I'm showing you on the left is basically just to indicate that the sample also gives us a variety of different spectral types, as well as masses, ages, and temperatures. So before Gaia Data Release 2, our knowledge of white dwarfs across the whole sky was very patchy, as you can see in that figure. Whereas after Data Release 2, we have almost full sky coverage of white dwarf candidates. This catalogue from Nicola Gentile Pisillo has created a set of hundreds of thousands of candidate white dwarfs from Gaia. And in the HR diagram, you can see that they've been given this parameter PWD, which is the probability that each source is a white dwarf from Gaia, which is a great starting point to be able to target spectroscopic follow-up. So we chose 40 parsec as our volume kind of cutoff, mostly because, as you can see in this plot, the white dwarf luminosity function kind of tails off at around magnitude 16 or 17 absolute magnitude, which corresponds for a white dwarf at 40 parsec to the kind of Gaia limit, which means that if we were going out any further than 40 parsec with our volume, we would start to potentially miss some of the very coolest and oldest white dwarfs. So the HR diagram on the left shows all Gaia sources within 40 parsec, not just white dwarfs. And then in blue, I've overplotted the white dwarf candidates from that catalogue that I mentioned before. So we had 1,083 white dwarf candidates within this volume selected in that catalogue. And that means that compared to all the main sequence stars in that volume, roughly 6% of stars in that 40 parsec volume are white dwarfs. Before Gaia Data Release 2, just under half of those white dwarfs in that volume were confirmed with spectroscopic follow-up. So between 2018, Gaia DR2, and now we have observed the other 600 white dwarfs to confirm their spectral type. So I've just shown on the right here the main different spectral types of white dwarfs. There's a lot of variability there, and the main things to consider for white dwarfs is whether they have a hydrogen-dominated atmosphere layer or a helium-dominated atmosphere layer, which are denoted dA or dB. And being able to identify which one of those we're looking at for our white dwarfs means that we can fit them with tailored atmospheric models to get their accurate temperatures, ages, masses. This HR diagram in the middle shows all of the spectroscopically confirmed white dwarfs within 40 parsec with their primary spectral type composition. And we find the space density of white dwarfs is about 4 times 10 to the minus 3 per cubic parsec. So all of the white dwarfs that we've confirmed within that volume were just selected from the catalogue, which did a cut around the white dwarf area of the HR diagram. But that doesn't mean we found all the white dwarfs within 40 parsec. So there are definitely some white dwarfs missing from the Gaia sample. You can see on this plot that I've pointed out some of the already previously known close unresolved in Gaia white dwarf plus main sequence binaries, and they kind of sit all over the place on the HR diagram. Some of them are just completely on the main sequence because the main sequence star in the optical dominates the flux so much. Some of them are sort of in between the main sequence and white dwarf track. So this plot shows that if we plot an HR diagram with the Galax UV photometry instead of a Gaia color, that is not enough to identify the white dwarfs in these binary systems, even though white dwarf flux peaks in the UV in most cases. There are still many M dwarfs with an excess in the UV due to activity. So we can't really identify these white dwarf main sequence systems that way. There are 4 known white dwarf M dwarf close binary systems within 20 parsec, and these were all found through radio velocity surveys of M dwarfs where a 0.6 solar mass companion was identified, which is not visible in the optical, so it's probably a white dwarf. And if we know of 4 of these types of systems within 20 parsec, that's roughly 4% of that volume being missing from the Gaia search. So if we extrapolate that out, that's quite a large amount of systems, at least, missing from our Gaia search. So I'm just going to quickly go through some of the key results from our sample. So first of all, I wanted to look at what fraction of white dwarfs had at least one companion, whether that's a white dwarf companion or a main sequence companion. I did this in 2 ways. I looked at the sources that were resolved in Gaia and those that were unresolved in Gaia. So to search for resolved binaries, I did a cone search around all of the white dwarfs within 40 parsec to check to see if there are any systems that would be bound. The plot on the left shows the tangential velocity difference against the separation of the binary pair. And the dotted line, anything to the left of that is likely to be in a bound binary system. What we found from this, which was already kind of predicted from smaller volume samples of white dwarfs, is that the number of wide white dwarf plus white dwarf systems is 10 times fewer than predicted by binary population synthesis models. We think this could be due to the white dwarf becoming unbound from its binary as it goes through its evolution of the main sequence, but that still doesn't really explain quite how few of these systems we see, so we're not really sure what's going on there. And the number of white dwarf plus main sequence wide binaries is as we would expect from these models. Additionally, I've shown on the right the same HR diagram as before, and I've highlighted the region where we would search for double white dwarf systems that are unresolved in Gaia. They appear overluminous on the HR diagram because they're 2 white dwarfs combined together. So it's quite easy to find them in that way. And then we can follow them up either using Gaia astrometric solutions if that's available, or if they have spectral lines, we could do radio velocity searches, which have been done in some cases for the warmer white dwarfs. So overall, with these searches, we find that at least 19% of white dwarfs are part of a multiple star system, but the number is probably higher than that.
Okay, Mairi, you have 3 minutes.
Okay, thank you. So we also found that there was a low mass issue for cool white dwarfs. We expect white dwarfs to stay at a constant mass as they cool, but now that we've been able to look at these cooler white dwarfs, we can actually see that the masses are underpredicted, which is what's shown in the histogram on the left. And we think this is due to an issue with modeling. The opacities of the white dwarfs slightly incorrect, but we wouldn't have been able to identify this issue without a volume limited sample looking at the cooler white dwarfs. And the final exciting kind of science thing that we've got here is the origin of magnetism in white dwarfs. About 1 in 4 white dwarfs harbors a magnetic field, and the origin of that is kind of debated. But by looking at the 40 parsec sample, we're able to see that as a white dwarf ages and cools down, there is an onset of magnetism. So you can see in the plot that the filled in dots and the dots with lots of circles around, which correspond to magnetic white dwarfs, there are more of them at higher, or like larger ages. And this could imply that some mechanism is causing white dwarfs to become magnetic as they age. This could be due to the core crystallization of a white dwarf as it cools, inducing a dynamo, which could create a magnetic field, but that's still something that's being studied. Oh, sorry. So some open questions I wanted to briefly cover, maybe for the breakout sessions, is how do we find all of the missing white dwarf main sequence binaries that were not in the Gaia search? And what fraction of M dwarfs, for example, have radial velocity measurements in a smaller volume? So we could check them to see if they have white dwarf companions. Additionally, how many white dwarfs have planets? I think this is a great question to ask with a volume sample because they're so close by that we can actually see resolved planets from things like JWST. What is the precise fraction of white dwarfs in binary systems? We have some idea of that, but it would be great to get a more robust number. And how do we extend out to larger volumes where Gaia will start to miss some of the coolest white dwarfs? So I wanted to quickly acknowledge all of the people that have been involved in creating the 40 parsec sample. I just kind of came in at the end and did all the final analysis. So thank you to all these people for helping put that together. And I'll leave my summary here and take any questions. Thank you.
Hey, thank you, Mairi, very much. And I wanted to apologize for not introducing you at the beginning.
It's okay.
And I also want to note that the reason Mairi is remote is that she was just out in Southern California about 2 months ago. She wasn't able to swing another trip quite so quickly. Okay, so I think what we're going to do is just hand around the mic here that this speaker would actually be using so that she can hear the questions directly.
Hello, Zachary Hartman from Gemini. So you may have mentioned this and I may have missed it, but for the systems that you're saying, the wide systems that you're missing in the white dwarfs binaries, what is your definition of wide?
Something that is resolved in Gaia. So I think, yeah, that the on-sky separation is, I'm not sure exactly what it would be, but let me go back actually, because I can check here. Yeah, so they're still wide even if they have a projected separation of just tens of AU or maybe 100 AU. So only the very, very tightly bound binaries would be considered unresolved.
Will Best, University of Texas. What have you learned about polluted white dwarfs so far from your sample?
Yeah, so I guess for context, for people who don't know what that means, polluted white dwarfs are white dwarfs that have accreted exoplanetary material, and you see that as metals in the atmosphere, like in this plot here with the 2 calcium lines for the DZ. So we found that about 20% of white dwarfs are polluted in the optical because all of our spectroscopy is in the optical. That number gets slightly higher when you look in the UV. But yeah, we found that most white dwarfs that have pollution accrete roughly chondritic material, so similar to the solar system. And most of them only have accreted a couple of metals, maybe 1 or 2. But we think that that number will get higher if we used higher resolution spectroscopy than what we could currently done.
Okay, thank you, Mairi. Let's thank our speaker again.
I am.
Yes.
Okay, I am.
So you need to put this on.
Thank you.
So our next speaker is Jose Caballero, Jimenez.
Yeah, whatever.
Whatever, I'll put somebody else's talk up.
Yep. Carmenes, can you hear me? Carmenes, yes, can you hear me? Hello, sir.